Okay folks, welcome back. So this is video number 27 in this series, this playlist, where I'm demonstrating how to conduct statistical tests, different types of statistical analysis using R and R Studio. So the playlist focused on kind of some pretty much basic frequentist statistical tests. In the previous two videos, we looked at the t-test, so a test that we would use when we're comparing the two groups, looking at differences in mean scores for each of the two groups. And in this video, what I'm going to do is demonstrate how to conduct one-way independent groups, ANOVA. So ANOVA, which stands for analysis of variance, is a type of statistical test that we use when we want to compare the means of different groups on some dependent variable, where we'd use the t-test to compare the mean scores for two groups. We'd use ANOVA most commonly if we wish to compare three or more groups. So if you've got three groups or four groups or more, we'd use ANOVA as the test we would do in order to see if those groups differ significantly in terms of their mean score. So the t-test and ANOVA are similar, but they don't exactly work in the same way. The t-test sort of more directly compares group means, whereas ANOVA compares variability around group means. Okay, so what I'm going to focus on in this video is demonstrating how to conduct a one-way independent groups ANOVA. That's probably the most basic type of ANOVA design we could use. So we've got one independent variable with three or more groups, and we're looking to see if those groups differ on some dependent variable. Okay, so we could have more complex designs such as two independent variables and look to see how the groups differ. Mixed designs where we've got independent groups and repeated measures. In this case, it's just an independent groups design. So we've got three groups, different participants in each of the groups, and only one independent variable. Okay, so I'm not going to get too much into the technicalities of explaining ANOVA and stuff like that. I've got other videos on my YouTube channel that you can look at to see that. But I'm gonna load the tidyverse because it's got a lot of useful packages that we might want to use. In this case, I'm not necessarily sure I'm going to use anything from. Maybe I'm going to use something from dplyr to manipulate the data in some way. But most of the functionality, most of the methods and functions I use in this particular video will be things that are included in the base R installation, essentially. So the data set I'm going to use is a data set. I've got it saved in the folder for the working directory that I'm in. It's called puppies.csv. Where are you? There it is, puppies.csv. I'm gonna use the read.csv method to load up that particular data set, puppies.csv. I'm going to save it as a data frame object, so you can see I've used the assignment operator. I'm going to call it df, short for data frame. I'm doing the read.csv, and then I'm passing the name of the CSV file in my working directory. Spelled exactly as it is, saved as a CSV file, like a spreadsheet, a comma separated values file. So this data set is one that has been made openly available by Andy Field. He uses it in his textbooks, introduction to stats using SPSS, using R, things like that. It's a very small data set. It's possibly made up data, I imagine it is. But it's kind of useful to just demonstrate how to conduct a one-way independent groups ANOVA. So I've just run that and imported the data, and you can see here in the environment here, I've now got an object which is a data frame called df. There's 15 observations of 3 variables, and if I run the head method there, we can see what those variables are. So we've got one called person, and that's just a number, like an ID number for the participant, 1 to 15. One called dose, which is a categorical variable, and there's 3 levels, 1, 2, and 3. I'll explain what those mean in a second. Another one called happiness, and this is like a numerical value of measuring how happy they are from a scale, 1 being not particularly, to 5 or more, maybe being quite happy. Okay, so the idea behind this particular data set is that people were exposed to a puppy, so they were allowed to interact with a puppy for different lengths of time. So there's level 1 of dose is control, so they weren't allowed to interact with the puppy. Level 2 would be they were allowed to interact with the puppy for 15 minutes, and level 3 is they were allowed to interact with the puppy for half an hour. And then they filled in some sort of questionnaire about how happy they felt, and I guess the idea is that interacting with a puppy makes you happier or something like that because they're cute and they're fun, essentially. So toy example, made up data, very small data set. But this is our data set. Dose is the categorical variable with 3 levels that is going to be our independent variable that we're going to compare, and happiness is the dependent variable, the how happy they are with the scores that we're going to look at as our dependent variables. So we want to see if these 3 dose groups, categories, differ in terms of their happiness significantly. But I'm going to do the glimpse command on the data set. And I always like to do this because it's quite useful, because it kind of lists out our data. I mean, this is the entire data set because it's so small. You can see we've got 15 participants. We've got 5 of those participants are in the control condition, 5 are in the 15-minute condition, which is level 2, 5 are in the 30-minute condition, which is level 3. And then we've got their 15 happiness scores for all these different people. It looks like it might have been measured on a scale of 1 to 10. We've got like a 7 there, a 6, a 1, that type of thing. So higher scores, happier person. But the main reason I ran the glimpse command was so we can see the data type where we've imported the data set. We can see they've all been imported as integers. So we want our happiness, our scale variable, to be a numeric value. So integer is fine for that. But dose, remember, although they're dummy coded using numerical values, what level, category 1, category 2, category 3, they're actually categories of factors, and they've been imported as integers. So we're going to need to wrangle that a little bit to change that. So I've demonstrated this type of thing before. I'm going to use a slightly different method. So I think in previous videos I've shown how you can convert a numeric variable to a categorical variable, or a factor as it's often referred to in R, using the as.factor type of method. I'm going to do it slightly different this time, and I'm going to create a new variable and append that to our data frame and call it dose underscore cat, so dose categorical. And the way I'm going to do it is using the cut method, and I'm going to supply a number of arguments. Okay, so I've specified df and then the $sign dose cat. So I'm saying the data frame, the object df, and we're appending to it a new variable called dose categorical, dose cat. I could have just called it dose and replaced the numeric values in dose with labels as a category. But I've said this, I think, in a few videos previously. What I often like to do is leave variables, the original variable alone, and create new versions append to the data set, just in case you need to go back and change anything at a later time. I don't particularly like to overwrite existing variables if I can avoid it. If you've got a large data set with lots and lots of variables, you might not want to do that, but in this case we don't. Okay, so, and then I'm using the assignment operator, and then I'm using this cut method, and the arguments I'm passing are, I'm telling it which variable I want to use the cut method to convert to this new dose categorical variable. So df$dose, notice it's spelled with a capital in the data frame, so I've spelled it exactly the same way, uppercase D, lowercase o, s, e, and then a comma, then 3, so I'm saying it, telling it there's 3 levels, and then a comma, then I'm saying labels equals, and then C to tell it it's to concatenate, tell it's categorical, and then I've passed in 3 strings, 1 for each of the 3 levels that we're specifying. So level 1 is going to be control, level 2 is going to be 15 minutes, level 3 is going to be 30 minutes. So let's run that. Okay, and hopefully that's worked. And if I run the glimpse command again, we should now see we have this fourth variable doscat, and it's shown as the data type is FCT or factor. And you can see there we've got the first 5 are control, which was level 1, which is what we wanted. Then the next one's a 15. So that seems to have worked okay. Right, so before we run the ANOVA to compare these 3 groups in terms of the happiness scores, let's just obtain a little bit of descriptives first. Let's get the mean scores for each of the groups so we can see if they do differ. That's just to eyeball it before we actually run the null hypothesis significance test we're going to do. So what I'm going to do is I'm going to use the aggregate function from the base R installation, and I'm basically saying take the happiness variable df $happiness, and then by equals list df $doscat. So I'm saying effectively aggregate happiness scores by the dose categories, and then fun equals mean. So the function I want it to return is the mean. So what this should do, if I run that, is it should return in our output window below in the console, should return the mean scores for each of those groups. Remember, they're very small samples, only 5 participants in each group. But what we can see when we look at this is we've got a mean happiness score of 2.2 for the control group, a mean happiness score of 3.2 for the 15-minute group, and a mean happiness score of 5 for the 30-minute group. So they do differ, and they seem to increase with the more exposure to a puppy. But obviously, to test whether these differences are statistically significant, we need some sort of statistical model to do that. So we're going to do the ANOVA to compare these 3 groups. Okay, so what we'll do is I'm going to use the pipe operator of the type we see in the tidyverse. And I think I've said before, I kind of like the syntax that we're using for that, and it's an intuitively sensible way to kind of to logically, I think, set out your arguments, your parameters. So what I'm doing here is I'm saying take the data frame, then I'm using this pipe operator, and then pipe it into, and the base R function for fitting an ANOVA model is AOV. You can see there the comments have popped up, so you can see where I've hovered my cursor over AOV, you can see that it tells us the arguments that you need to specify. So you've got formula, data, projections. Some of these are optional, but you certainly need the formula and the data to get anything out of it. Okay, so let me move that. Let's have a look at it. So I'm saying AOV, then I'm opening parentheses, and I'm specifying using these, what are often referred to as R-style formulas. I'm specifying the formula that we want to use. So on the left is our dependent variable, on the right is our independent variable. So we're saying happiness, and then we've got the tilde, and then dose cat. So we're saying happiness as a function of dose category. Okay, so that's our model formulation essentially. Then I've put a comma, and then I've specified data equals dot. So in most cases when you're doing these tidyverse pipes, you've already said what the data frame is, the data you want to use when you specify DF, and you don't usually need to say it again. But with some of these statistical analysis functions, such as ANOVA and the t-test, you do have to specify the data. If we didn't include this data equals parameter here, it would kick up an error, it wouldn't work properly. And all I've done is put data equals dot, and that's basically shorthand for just referring it back to the data frame here that we want to use. Okay, and then I've got another pipe operator, and I'm asking it to print out a summary of our ANOVA model. So let's run this, see what we get. Okay, and you can see in the output window below there, we've got our dose category. It gives us the degrees of freedom, the sum of squares, the mean square, which is useful for just calculating the F value. So if you take the mean square here, 10.067, and divide it by 1.967, you will get this value here, which is our F value, the F statistic for the analysis we've just conducted, 5.119. And the thing we're interested in, we've got our F value, we've got our P value. The thing we're interested in is have we got a statistically significant difference between these groups? And what we can see is we've got a P value of 0.0247. So it is highlighted here with an asterisk to tell us it's significant at this level, at the 0.05 level, which is a commonly used threshold of significance, alpha level, in many scientific disciplines such as psychology. So what we're seeing here is we have a statistically significant ANOVA model, and it's telling us that these three groups differ significantly in terms of their mean happiness score. The problem we've got with this, though, is, as anyone who's ever done ANOVA before will know, is ANOVA is an omnibus test. So we've got this significant F value. It tells us that the groups with the highest and lowest mean differ significantly, but it doesn't provide us any information about whether any of the other groups differ significantly from each other. So we can see that the lowest mean is the control group, the highest is the 30 minutes group. So our significant ANOVA, we can infer that at least the control and 30 minutes group statistically significantly differ, and the 30 minutes has a significantly higher happiness score, but it doesn't tell us whether the control and 15 minutes differ significantly or whether 15 and 30 minutes differ significantly. Okay, so what we need to do is do some follow-up tests. To obtain that information, we need to conduct some pairwise comparisons of all the groups. But when we do that, we need to adjust the threshold for significance that we accept, because we're conducting multiple comparisons, and that inflates our chance of making a type 1 error, of us thinking that we found a significant difference when we haven't, in fact. So what I'm going to do is, there are a number of different ways you can adjust the p-value when you're doing multiple comparisons, such as the Bonferroni correction and things like this, Fisher's least significant difference, stuff like that. The one I'm going to use here is Tukey's HSD, Tukey's honestly significant difference. And what that's going to do is I'm going to run the ANOVA model again with Tukey's HSD, and it's going to print out a table of pairwise comparisons. So it's going to compare control with 15, 15 with 30, control with 30. Okay, so let's run that. And to run that, I've basically done the same command as before, but rather than asking for the summary, I've asked it to provide Tukey's HSD. So specifying our data frame, piping that into the AOV ANOVA formulation model, happiness as a function of our dose category. We specified the data we want to use, and then we're saying give us Tukey's HSD for those multiple post-hoc comparisons. So let's run that. And as you can see, the output is slightly different before. It gives us an adjusted p-value. It gives us the difference between our groups, and we can then compare those to see if they're significantly different. So if we look, this first row here, we're seeing 15 minutes compared to the control, and we're seeing we've got a difference of 1 and a p-value, adjusted p-value of 0.516271. So not a significant, so we can still interpret these at the 0.05 level. So what we're seeing here is we've not got a significant difference between 15 minutes and the control condition. If we then look at the second row, which is comparing the 30 minutes with the control condition, we can see we've got a p-value of 0.02 if we round that to 2 decimal places. So as we kind of previously knew, they're the groups with the lowest and highest mean, and they've got a mean difference of 2.8, and they are still statistically significantly different. The third line here is comparing 30 minutes with 15 minutes. We've got a mean difference of 1.8. We've got a p-value of 0.147576. So 0.15 if we rounded that to 2 decimal places. So again, if we use 0.05 as our threshold of significance, not a statistically significant difference between those two groups. So although we got our ANOVA, our significant ANOVA model, we then had to do these follow-up tests And what they've told us is there is only two of those groups are statistically significantly different from each other, and that's the control and the 30 minutes. 30 and 15, although their means differ a little bit, they're not significantly different, and 15 and control are not significantly different. Okay, so one last thing I was going to do was just quite useful. I'm going to run that again, the 2 keys HSD. Up to here is the test we just ran. We fitted our ANOVA model, we asked it for multiple comparisons, and then I've just piped that into a plot call using the base, not using ggplot in this case, just using base R plotting function. If I run that, it gives us kind of this nice comparisons, difference in mean levels of dose category. You can kind of see where they overlap and things like that. So the differences between the two could be useful. It might be useful. There are other probably better plots you could use, but that's it in a nutshell. So that's the simplest design we could use really when running an ANOVA test. So an in one-way independent groups ANOVA model. I'm not sure whether I'll do any more ANOVA in this playlist series. I could do a repeated measures ANOVA, could do mixed design ANOVA, looking at interactions and all that sort of thing. But I am still trying to keep it quite basic. And I think what I'll do to finish off this playlist, because it's already kind of 27 videos long, is probably do some linear regression and multiple regression. And that will pretty much finish it off. Okay, so I hope this was interesting and useful. Thanks for watching and listening, and I'll record another one of these videos and upload it soon. Thank you.